This video was totally unplanned. When I accidentally stumbled upon the effect presented in this video, I couldn't believe this was even possible. In fact, I am still not 100% sure the explanation I'm going to give for what is happening is the correct explanation. Yet this is the best explanation I could find. Automotive spark plugs are a great budget-friendly option for making high-voltage vacuum feed-throughs. When mounted on a thin lead washer, they produce a vacuum-tight seal which is good down to at least 10 to the -6 torr, or even better, and they are even compatible with moderate baking. Then as long as one is using them for voltages of no more than about 15 kilovolts, and more importantly, only for positive polarity voltages, then they will work perfectly fine, and one will never encounter the issues described in this video. However, for my upcoming project, I needed a vacuum feed-through capable of handling voltages up to -30 kilovolts. So why not use a good old spark plug? What could go wrong? Well, the first problem was the insulation surface electrical breakdown observed at slightly over 15 kilovolts. This is an easy problem to solve, though. Just use a different model spark plug with a longer insulating sleeve. They do handle 30 kilovolts just fine. Or maybe attach an additional insulating disc, like this, with a suitable vacuum-compatible adhesive. With the electrical breakdown problem solved, we are now ready to discover something very unusual. First, let us try to apply a positive 30 kilovolts to the spark plug. Nothing much happens. This is why I said that using them for positive polarity voltages would usually not cause any problems. Now watch what happens when we apply a negative polarity voltage. Starting with a certain voltage value, we now have current flowing through the vacuum. You can even see the high vacuum grease and the fluorine rubber gaskets inside the chamber fluoresce under the electron bombardment. Isn't this bizarre? Obviously, there are no thermionic emitters in the chamber, nor are any carbon nanotube emitters or anything of that nature. So what is producing the current? I was completely puzzled when I first saw this happening. Remember, this is happening in a reasonably high vacuum of about 10 to the -6 torr. My initial theory was that maybe the electron emission was happening because of that tiny gap between the central electrode and the outer alumina shell, like a series capacitance circuit where the capacitance values are very different, and hence the entire potential difference would end up applied across the narrow gap between the metal electrode and the insulator, thus producing the electric field high enough for field emission? By the way, when reading about electron field emission, they casually mention the electric field required of the order of hundreds of megavolts, or even a few gigavolts per meter. This is hundreds of kilovolts or single megavolts per millimeter. When one is playing with potentials of 30 kilovolts or less, it is hard to imagine that there could be electric fields anywhere in the test system high enough for producing field emission. I then decided to simulate the spark plug. Sure enough, the electric field inside of that narrow gap was huge, and the value was definitely enough to produce field emission. Great, problem solved. Right? Well, not quite. Field emission would indeed happen deep inside that gap. However, the emitted electrons would have no chance of exiting out of the gap. They would just accumulate on the nearest insulator surface, thus reducing the electric field in the gap and eventually forcing the field emission to stop. So no, this wasn't the source of the current in the vacuum chamber. Another theory was that maybe a very small electron current was hitting on the vacuum grease, causing both fluorescence and ionization. And then the liberated positive ions were hitting on the cathode, thus emitting more electrons. I then added a shield hoping to break this cycle and greatly reduce the current. Yet the shield made no difference. It just turned my poor spark plug into a fancy electron flashlight. I then made a completely enclosed shield, and this didn't help either. The spark plug current was still about the same, and also the shield current was the exact opposite of the spark plug current, It was becoming obvious that the current was being produced entirely by the spark plug. But how could that be? It was time to go read some books. This is the book I found. It is a translation of a 1966 Soviet book about vacuum insulation and an electrical breakdown in vacuum. Interestingly enough, this is apparently a machine translation. So forget about Google Translate. They already had machine translation working back in 1970s. Anyway, the book describes exactly what I believe was happening in my vacuum chamber. Dark vacuum currents from the cathode. These currents do not depend on vacuum pressure, as long as the pressure is already low enough to eliminate the gas discharge regime. And these currents originate from the cathode when the electric field around it is high enough. The main source of the current is believed to be electron field emission. Yes, the one which normally requires those gigavolts per meter electric fields. These fields are produced around the tiny nanoscale extremities on the exposed surfaces of the cathode electrode. They can be reduced by suitable surface treatment of the electrode, but apparently it is impractical to hope for eliminating them entirely. Also, the field emission is believed to not be the only source of these currents. There are other phenomena which may contribute, like the ionization of the adsorbed gases and contaminations on the surfaces of both the cathode and anode electrodes. Armed with this knowledge, I was then able to get rid of those currents by coating the tip of the central electrode with a drop of ceramic adhesive. Vacuum epoxy would have likely worked just as great. It just takes longer to cure. I was very excited to finally solve this weird problem. But this then created another problem right away. How do we actually make any real electrical connections on the vacuum side, such as to hopefully not produce a lot of dark current? The trivial solution is to just coat all connected joints with a suitable insulating layer. A thin coat of ceramic adhesive, vacuum epoxy, or FormVar solution, if you have any, will do the trick. To test this idea, I made a simple test fixture of a single nickel wire attached to the spark plug on one end, with the other end coated with ceramic adhesive. It worked great, producing very little dark current and no visible fluorescent spots in the chamber. Then, just out of curiosity, I cut the coated wire end out and repeated the same test. Look at it. This is almost unreal. There is a whopping 60 microamps current at just 10 kilovolts, produced by the exposed sharp tip of that wire. I was speechless. Who needs thermionic emitters or even carbon nanotube emitters when we can produce 60 microamps from just a bare nickel wire? Honestly, I don't even know what the catch is. Like, maybe this type of electron emitter is not repeatable enough or something, but here it is, producing 60 microamps of current. So if you ever need a vacuum electron emitter, the sharp end of a nickel wire will work just fine. So coat those exposed wire ends. Interestingly, nearly the same effect is achieved by applying a thin coat of solder on the exposed wire end. I would guess that the solder surface has a lot less of those sharp nanoscale extremities, thus greatly reducing the dark current. Still, I could always see the difference between the wire tip properly coated in ceramic versus the one just coated with solder. The latter was still producing like 500 nanoamps of dark current at 30 kilovolts. Not much, and definitely a lot less than the raw exposed tip, but still noticeable. The ceramic-coated tip had the vacuum chamber completely dark. Another solution is to bend the wire back, solder the joint, and then coat just the very end of the wire. Also, instead of coating the joint, one can slip over an isolating sleeve made from PTFE or alumina. This is a tricky option, though, as the sleeve needs to be both tight enough and also extend far enough beyond the both ends of the joint in order to work correctly. Otherwise, there is a risk of arcing going from the wire over to the surface of the insulating sleeve. Ask me how I know. The final option is to just leave the soldered joint uncoated. Yes, it will then leak a bit of dark current, but not that much, typically less than 1 microamp, which could be acceptable for certain types of projects. Thanks for watching.